Let's start at first with the purpose and classification of aircraft systems. Okay, as a purpose of aircraft systems exist to support, to control, to monitor, and to protect the aircraft and its occupants so that flight can be conducted safely, efficiently. An example of efficiency is the reduction of fuel consumption and reducing the strain on the engines or the stress on the engines, reducing drag, etc. And reliably under all operating conditions, such as under rain, icing, good weather. Their main purposes can be summarized as follows: enable safe flight, which provide pilots with accurate information about the aircraft attitude, which is the bank, the roll, okay, whether it is banked to the right and how many degrees or to the left. Altitude is the height from the sea level, okay, or from the reference point of the airport. Speed, which is airspeed, speed, vertical descent or ascent, and direction or heading. Okay, in order to allow precise control, also another, which goes hand in hand with the first sentence, is allowing precise control of the aircraft during different flight phases, and also preempt the early detection of abnormal or dangerous conditions in order to repair the fault or to troubleshoot the problem before it becomes more dangerous. Okay, like at times you have problems that require an immediate landing, emergency landing. Okay, so here you have the avionics system, which is the electronic system, which is the gear system, okay, the landing instruments, the hydraulic system, which controls the different parts of the wings, okay, the different, wing controllers, such as the aileron, the elevators, etc., the fuel system, and monitoring of the fuel electrical system. You have environmental system, ECS, which is responsible for the air conditioning and other things, anti-ice and de-ice systems to prevent the accumulation of ice on the fuselage, which can decay the lift and other aerodynamic properties during the flight, and auxiliary power unit, also emergency systems. Another purpose is to support aircraft operation, such as supply power for the aircraft, whether electrical, hydraulic, to move the controls. Controls again are the different parts, the different dynamic or moving parts of the wings, such as the rudder, the elevators at the tail section, and the ailerons, which allow the aircraft to roll, to bank to one direction, and pneumatic, which is responsible for the gears and the braking system, okay, on the ground during landing or during emergency abortion of the takeoff, okay, to operate the equipment, control the engines, such as the throttle and the fuel system, okay, adjusting the fuel flow via the throttles to control the power of the engines and propulsion systems, manage environmental conditions inside the aircraft using by controlling the different air conditioning systems. Second, actually that would be the fourth, because we have the previous page, enhance performance and efficiency. Okay, so optimizing fuel usage and reduce the waste of fuel and engine performance, meaning trying to maintain the maximum, the most optimal performance of the engine, improve aerodynamic efficiency via the flaps, the slats, the spoilers. Okay, now the flaps are the rear part of the wing, which is dropped during takeoff and during landing, okay, which in a way help decelerate the aircraft during descent, and also using the airflow for the lift to reduce the descent rate of the aircraft, but at the same time to decelerated. Okay, this is during landing. Now, during takeoff, it is used to maximize the lift to lift off, to help lift off the plane during takeoff. Okay, and the slats are the forward part, like you have the flaps are in the rear end and the trailing at the trailing edge of the wings, but the slats are at the front leading edge. Okay, so flaps are at the trailing edge and slats are at the leading edge of the wing. They both like are used, they are dropped together to maximize the lift of the airplane. And spoilers or air brakes to increase the drag in order to decrease the speed, the airspeed of the aircraft. Okay, so they work to reduce pilot workload and errors through automation, ensure passenger and crew comfort, like cabin pressurization and air conditioning. Pressurization is needed because as you go up in the altitude, the density of the air decreases. Okay, so a human cannot handle breathing or living at high altitudes due to low air pressure. That's why the pressurization of the aircraft is required to imitate the same conditions on the ground at level 0, at sea level, so to speak. Okay, or acceptable condition of air pressure when you are like on the ground, not on the air, miles away, miles up high. Okay, above the ground. Reduce pilot workload and errors through automation. Okay, ensure passenger and crew comfort, cabin pressurization and air conditioning to mild the temperature, the living temperature within the aircraft. Lighting, ventilation, and noise reduction. Also provide noise reduction by controlling the engines as well. Okay, and provide protection and emergency capability, fire detection and suppression, ice and rain protection, because ice can lead to an aerodynamic stall by increasing drag and reducing the lift on the wings. And finally, warning, alerting, and monitoring systems. Okay, to monitor, to warn, these are the indication systems. Okay, along with the instruments to indicate if there's a fault, if there's a problem, like an overheat of an engine, in order to mitigate or like to jump right at the problem and solve it before it can escalate to something even more dangerous within the aircraft. And monitoring systems, monitoring the performance, monitoring different via different sensors, the temperature, the oil pressure, the engine rotation, like N1, N2, etc. Second, classification of aircraft systems. Okay, you have at first classification by function. So, for example, flight control systems. These systems control the motion and attitude or the bankroll of the aircraft. Also, the elevation and like the noise up, noise down, pitch up, pitch down motions, okay, are controlled, for example, by the elevators. The rudder actually, along with the ailerons, control moving, like turning right and turning left. The ailerons alone, they control the roll. Okay, so when the aircraft roll or it banks at a specific angle in order to turn and to change its heading, okay, what happens is that a part which is a component of the weight becomes distributed, or it becomes divided into two components. Okay, so at first it was vertical. Now, when the aircraft turns, a component of the weight becomes horizontal, another component like vertical, in reference of the aircraft wing. Okay, and you have the weight, which is like the horizontal and vertical component added together. The weight, it is vertical in reference to the ground, not to the aircraft. So the horizontal component is what moves the airplane to the right or to the left. This is how it skids to the right or to the left, or it turns to the right and to the left. Okay, now the elevator, what it does is pitching up and down the airplane. So when it moves upward, okay, so the air pushes the elevator, pushes the tail via the elevator when the elevator moves upward, which makes the tail go down and the nose pitches up. Now, if the elevator goes down, the air would push it upward. So when the tail goes up, the nose of the aircraft goes down. This is how it pitches down. Okay, and it changes the direction. So the first motion, it would be climbing if there's enough airflow. The second motion, which is the nose down, it would be diving. Okay, and decreasing in altitude. Okay, so the primary controls, ailerons. These are the ailerons, the orange ones here. Elevator, that's the elevator. The rudder, which is the moving part of the vertical stabilizer here, okay, that turns or moves the aircraft right and left. It turns the aircraft right and left along with the ailerons. Now, the rudder is used during landing at times when you have a crosswind that pushes or throws the aircraft to one side and throw it off track from its alignment with the runway. So the pilot would correct this heading, okay? It would correct the alignment of the nose of the aircraft with the runway by applying a right or left rudder so that it would remain aligned to the runway during landing, but also during takeoff, because if you have a crosswind, it would have the tendency to move the aircraft sideways, which is dangerous. Okay, so the pilot would correct the heading, the direction of the nose by applying rudders so that it would remain on the center line of the runway all the way to the takeoff point. Secondary controls are the flaps, which are the gray parts here. They are lowered down in order to, again, increase the lift during takeoff and during landing. The slats are the front parts of the flaps, okay? The flaps are at the trailing edge of the wings, but the slats are at the leading edge. So they go down also, which along with the flaps, they maximize the lift, but they increase drag, okay? So usually they are used during takeoff and landing. You have the spoilers, which are the air brakes, parts of the airplane that goes up. Not in every aircraft they are available necessarily, okay, especially in heavy Boeing 737, 747, okay, in these types of aircraft it is needed to reduce the airspeed and by increasing the drag, okay, that would be the spoilers, another name for the air brake. And the trim is a small part of the different controls, okay, which is applied, you see, because if we are flying, the weight of the airplane would be going on one side all the time, okay? It's never the same weight. So you would feel the tendency to keep pushing up or pushing down. In order to reduce that, we apply a trim, which is a small part of, let's say, the elevator, so that instead of keep on pushing the elevator to pitch up the airplane in order to remain in a leveled flight, okay, we apply the trim so that a part of the wing would go down, okay, and it would stabilize the flight, so to speak, instead of us always applying the controls. Now you have the control mechanisms. Okay, now the control mechanisms, you have different types of controls. You have the mechanical, where the power of the pilot himself would be applied and would be needed in order to move the controls. That would be in small airplanes such as, the Cessna, for example. You would be applying by your own strength in order to change the rudder or to pitch up or down or to move or to roll the airplane. You have the hydraulic, which assists. So you would apply the force and the hydraulic system would move the ailerons and the rudder. That would be in larger airplanes where you wouldn't have enough force yourself, enough strength to move these controls. They would be so much heavier and they would have much more strain on your own muscles. You wouldn't have the ability to move these controls. They would be heavy, especially when you're flying a very heavy airplane. Okay? And finally, the most advanced system of all is the fly-by-wire, where you apply a command, and that command on the yoke, for example, which is the steering wheel, like the steering wheel in an aircraft, and that command would be read by a computer. The computer itself would go into an actuator and generate the motion. Okay, it would be like powered, it would read your motion and then amplify it and give the command to a generator. Okay, give the command, like it would be a generator or an alternator rather, that would move, that would rotate the rudder or the levels or the ailerons. Okay, this is what fly-by-wire again means. It would read, you have a controller that would read your input and then plug it into an actuator, which is it will convert it into an amplified signal that will actually control. So it would be the strength of that actuator, like a motor, that will rotate the different parts of the different controls of the wings. Classification by function, instrument and indicating systems. Okay, so their main purpose is to provide real-time information to pilots and crew concerning what? Concerning altitude, airspeed, turn or roll, how much is the aircraft banked, and also this would be the attitude. So if it's rolling, banking, or if it's horizontal, okay? But also if it is leveled, meaning if it is nosed up or nose down, if you're pitching up or pitching down, because especially during the night you cannot see the horizon, so you won't have any reference to your flight except for the instruments. That's why they need to be very reliable. Now, what are these instruments? You have pitot-static instruments such as the airspeed indicator or ASI that measures the airspeed, because the speed of the airplane is actually the airspeed, the speed of the air moving through it. Okay, so this is how you measure the speed. Unlike when you have a car, it's on the ground, you measure the speed of the car based on the rotation of the wheel. Okay, here your reference is the air. Now, another is the altimeter, which would define the altitude, okay, the height from a specific reference point of the aircraft, and the VSI or the vertical speed indicator. Now, the vertical speed indicator is, along with actually the attitude indicator, would define for you, would show you whether the aircraft is climbing or diving. Okay, because when we talk about the attitude indicator, which is part of the gyroscopic instruments, okay, along with the heading and the turn coordinator. So when the aircraft is turning, for example, the turn coordinator would give you an angle here, okay, now, and it would show up also on the attitude indicator. Now, if it is pitched up, so the yellow dot here would be in the blue zone. Pitched up meaning the nose of the aircraft is up. So it is forming an angle, positive angle, in reference to the ground or to the horizon. It would be like this. Okay? Now, if it's pitched up, it doesn't necessarily mean that it is climbing, because there might not be enough airflow for it to climb. Climbing meaning it means that it's increasing altitude. Okay? So, in order to verify it, we need to look at the VSI, the vertical speed indicator, should be showing a positive rate. This is what we call it. Okay, a positive value, meaning the needle is upward. So it's showing a positive vertical speed. And this is when you can confirm it is climbing, because it can be nose up, but yet descending during a stall. Or it can be nose up, but during a level flight, which is, by the way, almost during the landing. At times you would have it like near to the runway, in a level to flight. It is flying at the same level, not descending much when it's about to land, but yet the nose is up in order to increase the drag and reduce the speed of the airplane so that it won't hit hard on the runway. Okay? And at the same time, by the way, it would be increasing lift, so to reduce the descent rate during the landing. Now, again, so the attitude along with the VSI and the altimeter would be increasing in value. This would show you that the aircraft is indeed climbing, not diving. Now, during a dive, the nose would be down and the VSI would indicate a negative value, so the needle would be going downward, or it would be indicating a negative value if you have a digital VSI. That would be in the ECAS, okay, engine indication and a computerized system. Now, you have the engine instruments. Okay, what are the engine instruments? The RPM or tachometer, which would give you how many revolutions per minute the engine or the motor is rotating, just like the RPM of a car. Okay, especially you would see that in turboprop aircrafts. It would show you the revolution or the speed of rotation of the blades of the motor of the turboprop engine per minute. Another important indicator is the EGT. The EGT is the exhaust gas temperature. Okay, so it would show you if it is overheating or if there's a problem through by monitoring the EGT, okay, to check if it is within the nominal values or if there's something wrong. Another important indicator, very important, is the oil pressure. You see, when there's a problem with the engine, okay, the oil pressure would drop, usually. When there's a problem like a rollback or the engine is shutting down, okay, or you're having like a problem, what we call engine flame out, due to running out of fuel or due to a specific shutdown, like the blades have been broken, it's no longer turning properly, you would have an oil pressure problem. Okay, so these are the different warning and annunciation systems, which are very important to observe and understand the status and the performance of the aircraft during the flight. Power plant and engine systems, okay, they are required to ensure safe and efficient engine operation. You have the fuel system, the ignition system, engine control and monitoring, lubrication and cooling systems. So here, if you look at a jet engine, as we're seeing here, you have the air intake, which is like a giant fan that sucks the air to the inside. That would be the first stage, okay, from the external air. Now, then the second stage is the low pressure compressor. That would be fans that would compress the air so that it would become more dense, okay, and thicker on the inside of the engine. Another stage would be a high pressure compressor, also sets of fans. Some of them are stators, which means they are static fans, static blades, and some are rotor, which they turn and compress the air against the static fans. Okay, and they have like the cavities of the air between the blades would be even more tighter to increase enormously the pressure of the air on the inside. So the temperature of the air would drop enormously. Then you have a mixture of this air with the fuel system and an ignition. Then after it is ignited, and with this very high enormous pressure, it would explode, and the combustion would generate the exhaust, okay, a hot air rushing rushing with a very high speed and screaming outside of the engine. That would create the motion forward of the airplane. And when it moves forward with a specific speed, the air flowing against the wings would create lift. Okay, so this is how it works. So the exhaust, the exhausted hot air would be thrown out of the engine, going out with a very high velocity, and this is what will push the aircraft forward. This is, by the way, called momentum. Okay, so the mass of the aircraft times the velocity of the aircraft moving forward would be equal to the mass of the air being exhausted from the engine times the velocity of the air moving outwardly. Now, the air doesn't have that large mass, that large weight. So how to compensate in order to force the aircraft to move forward? You would have the air going out at a high speed due to that type of combustion after being mixed with the fuel. And this is what will create the forward motion, the forward force, along with the air flowing around the wings and the different fuselage sections. This is what will create the lift within the air. For electrical systems, which have the purpose of generating and storing and distributing electrical power, you have mainly the parts that play a role in this electrical system are the generators and the alternators. Now, they are slightly different. We'll explain that afterwards. You have the batteries to store the power. You have the APU, auxiliary power unit, by which you can restart the engine during mid-flight if there's a problem. You have the bus bar and circuit protection, okay, in order to protect against electrical surges, to prevent incendiary events, okay, and fire events or short circuits. Lightning, also lightning protection, and avionics power. Avionics are the different electronic systems for measurement and monitoring. Now, if you look at this graph to the right, you have the different circuit. You have at first the different, circuit breakers. Circuit breakers in order to protect against an electrical surge, and these circuit breakers are displayed between the primary bus and avionics bus. Now, the primary bus is connected to different controls, and then to the right it's connected to different monitoring systems, okay, like fuel quantity indicators, flashing beacon, pilot heat, different switches and different indicators for different systems of the airplane. You have, for instance, here indicator of the battery power, the alternator that generates power here, okay, connected to the circuit breaker, and circuit breaker pull off, push to reset, like this one. You have the starter or the igniter, battery contactor, okay, that can switch automatically to the battery in case there's a problem on board, oil pressure switch, okay, the battery on, battery off system, etc. Okay, we're gonna dive deeper afterwards to understand the different parts of the electrical system. 5. Hydraulic and pneumatic systems. Okay, so you have high force power transmission. For that high force power transmission, it is required to have the hydraulic system so that it can relay the power, like the control from the pilot to, or like the command from the pilot all the way to the different controls, different parts of the airplane, such as the flaps, the ailerons, the rudder, the elevators, etc. Okay, you have hydraulic pumps, actuators, reservoirs, pneumatic and bleed air systems. 6. ECS, or environmental control system. It controls the internal aircraft environment. It is responsible for cabin pressurization to make sure that the pressure of the cabin is comfortable for the different, the crew, the flight attendants, and the different people that are on board. You have the air conditioning system through the gasper, the ventilation system, etc. 7. Landing gear and braking system. It supports the aircraft during ground operations. Also responsible for landing gear extension and retraction. Retraction during takeoff, of course. Braking and anti-skid systems to prevent the airplane from sliding on the runway. Steering and shock absorption. You have a damper also to absorb the shock during landing, during touchdown. Also, you have protection and safety systems, detect and mitigate hazards, okay, fire detection and extinguishing system, especially within the engine, okay, when you have a problem with the engine, it's on fire, you have an extinguishing system that will turn off the engine. Of course, when that happens, there's no way to turn it back on, okay? And finally, you have ice and rain protection, which are the de-icing system, like the pneumatic, the de-icing boots that inflate and deflate in order to break the ice forming on the wings, on the front edge, the leading edge. And also you have overheat and smoke detection. So looking to the right illustration here, you have engine fire overheat detection system, the sensors that are within the engine. APU fire overheat detection system. APU again is the auxiliary power unit that is needed to restart the engine, whether on the ground or during flight if there's a problem, if they for any reason flamed out. And left and right pylon thermal switches, okay, aft equipment area thermal switches. You have rear and rear thermal switches, different thermal detectors, forward cabin, underfloor thermal switches, etc. These switches are required in order to turn off, for example, the power that's feeding, for example, the lavatory. The breaker would open up in case there was a problem of a fire or a short circuit or a kind of overheating. It will pop up in order to break, create an open circuit and prevent a fire if there was a surge, an electrical surge, and if the current increased to a specific level above the level tolerated by the circuit breaker would pop, because that would be an indication of something problematic going on, such as a short circuit, for example, or an electrical surge or overcurrent consumption, which can heat up the cables and cause a fire. Okay, this is another illustration for the different hydraulic systems. You have left and right engine switches. You have, for the fire here, you have fire extinguishing, MAU1, okay, left fire, right fire extinguishing agent bottle, okay, that are placed near the engines, the cartridges. Okay, a little bit more complex system. I won't go into detail. The power source, the fuel control shut off valve, etc. Okay, to control the fuel, to shut off the fuel, to display the fire alarm. Okay, you have APU fire extension, etc. Yeah, the different, that would be the extinguishing or a fire protection system within the aircraft. This is its architecture. Avionics and navigation systems. 9. Okay, their main role is to enable communication with the ground, to get vectors, to get different, the guidance in order to land, which runway, to get different information and assistance in case of an emergency, etc. Communication is very important. And for the navigation meaning understand where you are on the map, what are the different, what is the characteristic of the terrain that you're gonna land over, where is it located, and where you are, like your own heading in respect of that terrain. Okay, but also your attitude, your altitude, all of that is part of the navigation. Okay, mainly the navigation refers to, yeah, your own position on the map. Okay, so you have the navigation systems are the VOR, very high frequency open range radio, okay, which is like a checkpoint that you can cross, and it's not as accurate, but you cross that checkpoint as a reference that you're heading towards the airport, and then you locate the airport visually, okay, usually via the VFR if the airport if the airport or the runway is not equipped with the ILS. Now the ILS, or the instrument landing system, is made of two beams, like it's projecting two beams. One is vertical and the other is horizontal. Now the vertical beam is called the localizer. The localizer is necessary so that you can align on the runway. So you would see like a vertical line on your instrument. When it's moving to the right, you need to move to the right to align with the runway. When it's moving to the left, you need to move to the left. It needs to be centered on the display. The glide slope, the other beam, is the horizontal beam, which is the glide slope. Glide slope is like a how can I say it? A virtual plane. It's not virtual, like it's a projected plane, projected communication beam that once you track it, okay, on its center it has the maximum power, okay, you need to be going down that center. Now if you go below it, it goes up on the indicator. It means that you need to climb to intercept it. If it goes down, it means that you're way above the airport, you need to go down, okay. So this horizontal line needs to be at the center also of the attitude indicator usually. And as for the glide slope, the glide slope needs to be, which is this horizontal line, needs to be at the center of the attitude indicator, and the localizer also at the center. They need to cross at the center, which means for the localizer, you're aligned at the runway. For the glide slope, you are descending at the correct descent rate, so that you can be neither above the runway nor below the runway, okay. You are perfectly aligned and you're gonna land perfectly on the runway, okay, at the right position. And finally you have the GPS, which can locate you on the map. You can understand where you are, okay. You have the FMS, flight management systems, okay. Then classification by power source. So you have the mechanical systems, direct mechanical linkages, cables, rods, pulleys that are common in light aircraft. Here we're talking about the classification of different aircraft, okay. So classification by power source, you have the mechanical systems, direct mechanical linkage, cables, rods, and pulleys for light aircraft. Electrical systems, you have sensors, motors, avionics. These are for the instruments, okay, increasingly dominant in modern aircraft. Even the control is electrical, which is called, again, fly-by-wire. And the hydraulic systems, you have high force systems such as gear, brakes, and large control surfaces, okay, controlled by hydraulic power. Pneumatic systems, you have the bleed air for pressurization and anti-icing, the de-icing boots. Classification by level of integration, independent systems, standalone instruments or subsystems, okay, how they are integrated. Or integrated systems, meaning you have centralized monitoring, EFIS, ACAS, engine indicator and crew alert system, and ECAM, okay, that share data via aircraft data buses. Okay, what does that mean? For the independent systems, you would have one instrument for the attitude indication, another instrument placed right next to it, especially in the small airplanes, okay, for the altitude, one for the attitude, again, one for the airspeed. They are separated. Meanwhile, in the integrated system, especially in large aircraft, you would have, for example, the ECAS, which is the engine indication and crew alert system, On that display, you'd have multiple displays concerning the engine, whether the oil temperature, oil pressure, EGT, exhaust gas temperature, the N1 and 2 rotation. Okay, all of that integrated in one system. In one, of course, you have different sensors, but the display is on one display, on one single screen. That's the difference. Okay, and eCamp. Okay, so they all share data via aircraft data buses. Now, EFIS, by the way, is Electronic Flight Instrument System, and eCam is the Electronic Centralized Aircraft Monitor. Okay, so the eCam is the Electronic Centralized Aircraft Monitor, which will have in the middle the attitude indicator, but along with it to the left you'd have the altimeter, okay, the measurement of the altitude. To the right you would have, to the left you'd have the ASI, okay, the airspeed indicator. To the right you would have the altimeter that would display your altitude, along with also another display, which is a vertical display for the VSI or the vertical speed indicator. And within that same instrument, you'd also have what? The directional heading, okay, the heading. You would have, when you are using an ILS system, instrument landing system, both the localizer and the glide slope that should be centered to the middle during the landing. So different, also the third coordinator would be displayed on the eCam. So different displays have been integrated in large aircraft on one monitor so that you can check, you can have a situational awareness over where you are in flight and how you're heading and how is your performance when it comes to the ECAS, when you monitor the ECAS, okay? And also the eCam to check your altitude, to check your airspeed, even the different warnings such as the stall and other things, other behaviors of the engines are indicated on these integrated screens. That's why we call them integrated systems. You'd have one computer display like integrating different functionalities, different instruments at the same time. Meanwhile, for the independent systems, you would have different instruments that are stand-alone. They are independent. You have the airspeed indicator alone on one part. You have the altitude indicator also stand-alone and separated, etc. Here in this display, we see the pneumatic system, which is driven by hydraulics from the motors, the engines of the airplane, okay, that transmit the power via, again, hydraulics to apply pressure on both, on the gear, okay, on both wheel parts during the landing, during, to break them, okay, so they are also during retraction of the landing gear or pulling down of the landing gear. Retraction, of course, is right after takeoff. So this is like a small animation. You see the bleed, the overheat sensors here. You see also the APU is involved, okay, for cargo heat. Wing anti-ice, because the anti-ice, the de-icing system is driven by the pneumatics, especially in the Boeing 737 and, bigger aircrafts. Why? Because you have the de-icing boots need to be inflated and deflated in order to keep breaking the ice formation on the wings, which is like the inflation and the deflation are driven by the power of the engines, the motors, okay, as we see here. You also have the icing systems on the engines themselves that are also driven by the same power, okay, of the hydraulics. Usually, actually, the anti-icing on the engines is through the heat of the oil engine. This is what breaks down the ice. Okay, so it's a more complex system. You have the ground pneumatic. Also, it is connected to the same hydraulics, okay, for cargo heat. You have the wing anti-ice, both on the right wing and the left wing. So this is how it basically works. And of course, all the sensors that are responsible for measurement, and the instruments within the cockpit for monitoring the hydraulics and the temperature, okay, and whether to check if the icing system is working or not, okay, all the instruments that go along with this system, whether for monitoring or for control. Relationship between instruments and aircraft performance. Aircraft performance is directly monitored and managed through a variety of flight and engine instruments. Okay, so these instruments have the responsibility of data collection, of measurement, and you have the indicators within the cockpit are to display these measurements to indicate whether there's a problem or alarm. Okay, so these instruments provide the pilot with real-time data that reflects how the aircraft is responding to different controls, to control inputs, environmental conditions, and system limitations. Okay, among these instruments, of course, you have the altitude indicator and the VSI, which would indicate for us whether if the aircraft is climbing or diving. Okay, VSI stands for vertical speed indicator. Okay, if it is a positive speed, it means that the airplane is climbing. If it's negative, it means it would be diving, along with the altimeter that will indicate a gradual decrease in altitude during descent, or an increase during climb and during takeoff, of course. Now, you have also attitude indicator, you have the airspeed indicator. For example, by the way, during takeoff, the co-pilot would need to notify the pilot whether the VSI is positive or negative, okay? Or it won't be negative, it would be perhaps 0 or negative, okay? Which means that once the VSI indicates a positive value, it means that the aircraft is climbing. So the co-pilot would tell the pilot, positive rate or positive climb, gear up. So now it would be safe to retract the landing gears because the aircraft has a positive climbing rate. It means that it is increasing in altitude. It is taking off correctly. Okay, it's getting away from the ground level. Okay, it's climbing. Okay, now primary flight instruments such as the airspeed indicator, the altimeter, the VSI, vertical speed indicator, and attitude indicator allow the pilot to evaluate lift generation, whether the aircraft is creating lift. If it's creating lift properly, it means that it should be climbing correctly, okay? Altitude control, climb or descent rates. So climb rate, let's say 500 feet per minute. That would be a positive climb rate, or a minus 500 feet per minute. That would be a negative climb rate, okay? Negative descent, actually. Negative rate, but a descent rate, okay? Which means that the aircraft would be descending. It would be decreasing in altitude. For the first case, it would be increasing in altitude. And aircraft orientation, which is indicated by the directional gyro or the compass, commonly named, okay, which would give you the direction, the heading of the airplane in respect of what? Of the north vector, okay. Now from the north, when you rotate, okay, I think the rotation is, yeah, the heading would be measured clockwise in reference to that north. So when we talk about heading 90 degrees, that would be 90 degrees heading from the north direction, from the magnetic north, okay? Of course, the perfect north and the magnetic, there may be some degree of error between them, okay, that the pilot will have to account for. Now, for example, airspeed indication is critical for maintaining safe margins above stall speed and below structural or regulatory limits. Okay, what is the stall speed? Stall speed is the airspeed at which the air would no longer have a laminar flow around the wings. It is the speed, and it would be a low margin, okay, a low level of speed at which the air is no longer able to generate lift around the wings. So the aircraft would stall. It would lose its upward force vector, so to speak. Stall, it means it will start falling down to the ground. It's no longer generating lift. Now, it can either happen due to a large angle of attack, okay? So the air is no longer able to flow around the wings because most of the air is now dragging, causing a drag effect on the wing instead of lift. Or it can be slow flying speed during, for example, due to an engine flame out. Or another possibility, it would be the icing formation on the wings. It would degrade enormously the performance of the aircraft, causing a stall, okay, by increasing drag and reducing the lift properties of the wing, okay, because it would disturb the laminar flow of the air around the wing section. So it is critical to measure the airspeed in order to know whether you're above stall or stall speed or at the stall speed, because once you hit a stall, there's another warning system, by the way, within the aircraft. Other than the indicator, you have the stick shaker, which means that the yoke would start shaking violently to indicate that you are entering a stall. Okay, so in order to correct it, you need to lower down the nose by pitching downward, okay, by moving the yoke forward or the steering wheel forward to gain more speed to reduce the angle of attack, okay. Gain more speed by using the horizontal component of the weight of the aircraft as a forward force, okay, to make the airplane cut through the winds and to generate more lift. So once you gain enough lift by increasing the speed, the velocity of the aircraft, you would gain more lift. This is how you would be able to get out of stall, okay. But also, very high air speeds can be way dangerous for the aircraft. Why? Because it would damage its structure, okay. It would be structurally damaging, meaning that different controls of the airplane would start flying off, like even the doors of the landing gears would start ripping apart, okay. So it would inflict a structural damage, okay. That would be the overspeed. This is why you need to stay within the acceptable margins. But not only that, based on regulations, there are certain speeds that you cannot cross over, otherwise you'd be fined, even as an airline pilot. Okay, so while altitude and vertical speed indications ensure compliance with flight profiles and air traffic control clearances, okay, so you have different instruments for different measurements concerning airspeed, altitude, VSI, so as to remain within the regulatory confinements, okay, of flying, but also to keep the aircraft airworthy, meaning flyable and avoiding any structural damage while increasing the efficiency of the aircraft as well. Engine and system instruments further influence performance management, okay? So parameters such as the engine RPM or tachometer, which measures the number of revolutions of the blades per minute around the axis. The turbine, at first you have the manifold pressure, the pressure generated by the engine, the EGT or exhaust gas temperature, which is the temperature of the exhaust, okay, can detect an overheat within the engines. Turbine inlet temperature, okay. So turbine inlet is the section of the engine where there's the air intake, okay. So it is the head of the turbine, okay. Actually, no, not at the front of the engine, at the head of the turbine, okay, where the intake air is measured for the temperature, okay. So it would measure the turbine inlet, okay, where the air suction is performed. That would be measured temperature wise. The oil pressure would indicate whether the engines are properly running or not. So when you have a flame out, you would have a decrease a significant drop of the oil pressure, which means that the engine is not or is no longer running. Fuel flow also provides insight into the engine efficiency, how much fuel flow is being received by the engine, thrust output, okay, how much thrust is being generated, and thermal limits. Now, deviations from normal indications may require performance adjustments, okay, such as adjusting the throttle, power reductions, reducing the flow of the fuel to the engines, or emergency procedures. Let's say you have an engine on fire or an engine backfire. So the proper thing is to reduce the engine at first to idle, set it to idle, try to solve the problem. Now, otherwise, if it was not solved, you need to extinguish the fire, which will completely turn off the engine, and you cannot undo that in mid-flight. In modern aircraft, performance data is often integrated into electronic flight displays such as the ECAS, the ECAM, okay, and the flight management system or FMS, which constitutes the ECAS or engine indication and alert crew system, plus the ECAM or electronic centralized aircraft monitor, okay, enabling performance calculations such as takeoff distance, climb gradients, fuel consumption. Consequently, aircraft instruments serve not only as monitoring devices, but as essential tools for optimizing performance while maintaining safety margins. Aircraft system redundancy and safety philosophy. Now, why is redundancy very important? Because you see, for every system, I need a backup for it on the plane. Why? Because if you have a breakdown, you cannot fix the airplane in mid-flight. You need something running as an auxiliary, whether power or an auxiliary unit, okay? And to provide redundancy is for safety measures, so that in case an instrument broke down, you would have an alternative in order to monitor the performance and the attitude and other controls, like the status of other controls of the aircraft, and to have a situational awareness, to have to understand how your aircraft is performing, basically, okay? To check the performance, to check the different indicators, okay, on alternative instruments in case the main instruments broke down, so that you can still have control over the airplane, and especially during night flight, because you would not have a reference for the horizon when there's no visibility. So you need instruments to understand where you are situationally, so to speak, okay? So aircraft systems are designed according to a layered safety philosophy that assumes failures are possible and must be mitigated or reduced. One of the core principles of this philosophy is system redundancy, having more than one system running, which ensures that the failure of a single component does not lead to a catastrophic outcome. Redundancy may be implemented through multiple independent systems on board performing the same function. So, and why do they need to be independent? So, in case one of them shut down or broke, okay, or malfunctioned is the more accurate technical word, you can rely on the other being operational and still running, okay, independently. Because in case they were attached to the same cable, let's say, okay, in case you had two instruments and you have layers of redundancy, but let's say these two instruments are almost the same device but two different display, it won't work, because in case the main instrument shut down, both display would go out. That's why we need that standalone and that independency between the different instruments that are redundancy, that are the same thing, the same type of instrument but replicated, okay? The same instrument having, but we have two of that, okay? Two pieces of that on board, so that you can monitor and you can verify the performance via two main instruments. In case one broke down, you can still follow the other and rely on its measurements, okay, and remain confident that you are getting accurate values. So examples include dual or triple hydraulic systems. Also, it's not only the indication systems, but also the hydraulics. Multiple electrical generators like the APU, like the ram air turbine in case you have engine flame out, and we know that the engines is what generate power. It is the power generator on board during mid-flight. So in case both engines flamed out, you need an alternative power, and that is usually by deploying what is called the RAT or ram air turbine, which is a turbine that falls beneath the beneath the airplane. Okay, it's deployed from beneath, and the air going through it would generate enough power to keep running crucial, essential instruments that are very necessary in order to maintain, a situational awareness over the performance of the aircraft, over the altitude, the VSI, okay, necessary to make at least an emergency landing. Okay, you have two independent pitot-static sources, which are the same. This is actually the device that measures airspeed, altitude, and VSI. Very important. In fly-by-wire aircraft, you have flight control computers are often arranged in multiple channels with voting logic to detect and isolate faulty data. So if you have a faulty data, it would be relegated to another computer, to another processor to manage the flight, okay? Instead of relying on only one source of computing, which can be sending falsified measurement data. In addition to redundancy, system segregation or separating between systems is used to prevent a single event, such as fire or structural damage, from disabling or taking out multiple systems, especially redundant systems, simultaneously. Why? Because if you had a fire and you have two systems that are a redundancy, meaning they are the same thing but distributed among or divided into two instruments, okay, that do the same functionality. Let's say you had a fire. It can take out the original system and the redundant system as well. So you wouldn't have done anything because it would no longer be a reliable architecture. Why? Because you had taken out the same vital system twice, distributed among two separate instruments. So we need to ensure that if one instrument failed, its backup, that's the word I was looking for, should be working properly. Why? Because you had isolated its wiring and its installation from the first. They should be completely segregated and independent. So the failure of one should not take away or take out the other. Very important. Now, this includes physical separation of wiring, physical separation of hydraulic lines. So if one rupture due to the impact of a solid object or something breaking in the plane, the other one would not rupture. Why? Because it's positionally separated, okay, geographically within the airplane, or anatomically, to be more accurate, separated from the other hydraulic line. And also electronic components throughout the airframe. So you would have multiple computers distributed in different places of the airframe as a backup. That would be something usually done in fighter planes, okay? Multiple computers back up each other. Now, the safety philosophy also incorporates fail-safe and fail-operational concepts. Fail-safe systems revert to a safe condition following a failure. So if a failure took place, you have a fallback to another system that is a backup, okay? It might be the next best thing after the failure, okay? While fail operational systems continue to function normally despite certain failures, okay? Together, these design approaches ensure that aircraft remain controllable and safe under a wide range of abnormal and emergency conditions. As an example, let's say during landing the ASI for whatever reason had failed, the airspeed indicator. You have another device measuring airspeed, which is not actually airspeed. It would measure the speed of the airplane based on the ground. Okay, it's called the ground speed indicator. Okay, the GSI, if we can call it that. So how does it work? It sends signals to the ground, and it measures how long it took the signal to be reflected on the ground and then to get back to the receiver on the plane. Okay, this way you can measure the approximate speed of the airplane based on the ground. Okay, now of course in this case the aircraft should be close to the ground relatively. Okay, that would be during the landing phase, but that would be a backup. Okay, an alternative to the ASI in case the ASI had failed. That would be the fallback. Now the fail operational, that would be the fail safe system. Okay, the fail operational is that it continued to function normally despite certain failures, meaning you have a backup within the system. Yeah, it can be explained in different ways depending on the system again. Okay, like if I'll do without the jargon here, if I'll set it aside, okay, that would be like, for example, a fault within the hydraulic system, but you have another hydraulic pipeline, okay, that is driven by manually instead of the one driven by the autopilot. That would be, you would take over, disable the autopilot, and continue to fly manually on the second hydraulic line. Certification standards, FAA and EASA, okay. FAA is the Federal Aviation Administration, which is in the United States, and EASA is the European Union, okay, Aviation Safety and Agency. EASA is basically the one that governs flying in Europe. So aircraft instruments and systems must comply with strict certification standards established by regulations, regulatory authorities to standardize. Okay, this is mainly to standardize flying, so that it won't be that each agency would be, or each company, airliner, would be going on one level, like doing their own regulations. Okay, it would be standardized. The two primary organizations, again, are the FAA in the United States and the EASA in Europe. Okay, both authorities issue regulations covering aircraft design, production, operational limits, and maintenance. Okay, key certification documents include FAA Title 14 for federal regulations and the EASA certification specifications. These standards define requirements for system reliability, failure probability, environmental qualification, also the standard for creating, for designing airports, but that would be in another book other than this. Okay, now human factors, like how many hours should a pilot sleep before being allowed to pilot an airplane. Also, we know that drinking is not is prohibited for pilots. Okay, especially hours before flight. And continued airworthiness. Okay, airworthiness meaning is the airplane still flyable? Okay, and how many hours is it allowed, or how many cycles is it allowed to fly? A cycle is one compression decompression. Okay, so each time it flies and it lands, that would be one cycle. Now, instruments must remain accurate and readable under vibrations. This is another important caveat for the standards. Temperature extremes also should not block the instruments or prohibit the reading of different values such as the ASI, the airspeed, the altitude. It should not be generating errors due to extreme weather conditions. Okay, and we're mainly here talking about the pitot tubes, but other devices also follow suit. Okay, electromagnetic interference also should not shut down the capture and reading of values. on board by instruments, different values, different measurements, and also varying pressure conditions. Although FAA and EASA standards are not identical, they are largely harmonized. Okay, so aircraft certified under one authority can often be validated by the other with minimal additional requirements, facilitating international aircraft operation and manufacturing. Basic aircraft terminology and system architecture. Understanding aircraft instruments and systems requires familiarity with basic aircraft terminology and system architecture. What are the different systems on board and that make part of the aircraft? Okay, what are the different devices of these systems and the necessary jargon and terminologies that go along with these systems. An aircraft is generally divided into major structural components, including the fuselage, okay, that's everything within the airplane, like the airframe without the wings, okay, that's the fuselage, the wings, the empennage, landing gear, and power plant. Power plant is the engine, okay? Now, you have also the vertical stabilizer, it's part of the fuselage, and the elevators are part of the wings. The rudder is also part of the wing, you can say. Now, aircraft systems can be broadly classified into several functional groups. You have flight control systems, primary and secondary controls. You have the power plant, the engine generating power and propulsion systems. You have electrical power generation and distribution through the engine. Usually the engine is the same source of electrical power because it's at the same time a generator for power to drive the power, to feed different instruments on board. You have the hydraulic and pneumatic systems that also drive their power from the engine. Okay. Avionics and navigation systems, which are the different displays on board within the cockpit, and environmental control and pressurization systems, among which you have the air conditioner, the gasper, all of these systems that drive or control the environment, okay, the temperature and the pressurization, the air pressurization of the cabin. System architecture describes how these systems are arranged, interconnected, and controlled. Traditional aircraft rely on mechanically driven systems with analog instruments, so analog measurements. It's not digital. Meanwhile, you have digital data buses and centralized monitoring systems are different, okay? So you have analog instruments, while modern aircraft use integrated modular avionics, which means a screen that displays multiple measurements, multiple instruments at the same time. Okay, like digital data buses, you have digital data bus that collects from different instruments, and you have a centralized display, and you have centralized monitoring systems, mainly like the ECAS and the ECAM, the engine indication and the crew alert system, or crew alert system, and also the ECAM, which is the electronic centralized aircraft monitor that monitors the aircraft, monitors different instruments such as the altitude indicator, altimeter, ASI, VSI, etc. For the ECAS, it monitors the engines and the oil pressure, the oil temperature, etc. Okay, and the EGT, exhaust gas temperature, among other things that I might not have remembered at this moment. So, clear terminology and a structured understanding of system architecture allow pilots, engineers, and maintenance personnel to interpret instrument indications correctly, okay, diagnose faults efficiently, and correctly localizing or locating and isolating a problem and a fault, and operate the aircraft safely and effectively.